going to get started. So welcome to this talk. I hope it'll be a fun, quick, technical demonstration. Before we get into attacking serverless servers, I would like to make a quick shout out to the course that I teach for the SANS Institute, the Cloud Security and DevOps Automation course, or SEC 540. The reason I give that a shout out is a lot of the slides in this material come directly from that course. So if you'd like to learn more about security from a DevOps perspective, then this would be a great resource. Or if you're a security person who'd like to learn more about how the DevOps world works, it would also benefit you. So let me know if you'd like to learn anything about that course. I'm happy to give you more information after the presentation. Very brief overview of who I am. So I teach for the SANS Institute, but like most people who teach for the SANS Institute, that is a part-time job. My full-time job is being an application security engineer for Azure. Prior to being in security, I was a developer for Azure, and that is my background originally. I have only been in security for a short period of time. Here are some of my credentials that I've collected. The reason why the GCSA, by the way, is pending is I took the beta exam, and they won't tell anybody that they've passed until they release the actual exam. But that's the test for the course that I teach, so here's hoping I pass. So a lot of you probably coming in here as developers are probably thinking, okay, here's this security guy who's going to talk to us about security and how serverless is this terrible new technology that's plagued with security problems and that y'all are irresponsible for using serverless. So I want to dispel that notion right away. I love serverless. I love it as a developer who's been using it for 3 years in production, which is a fairly long time. I love it as an operations person who doesn't have to be called up at midnight every once in a while to reboot servers manually. And believe it or not, I love it as a security person. Serverless has some inherent valuable things from a security perspective. Not having to patch your systems means that we don't have Patch Tuesday. That's now AWS's responsibility. Not having large monolithic applications means we can break down our permission sets in such a way that we limit what we can actually access in the cloud at a very granular level. And because functions are theoretically ephemeral, that also means that you can't have long-term command and control servers. I say that is theoretical, as you'll see in just a moment. Because with any new technology, there are security concerns and, more importantly, misconceptions. And in this talk and presentation, I'm going to show to you all that it is possible to hack a serverless server. So at this point, you might be wondering, serverless server, isn't that an oxymoron? First of all, who are you calling an oxymoron? Second of all, it is not, because at the end of the day, serverless uses servers. It doesn't mean that we have to manage those servers, but at the end of the day, the code that we define gets loaded up on a virtual machine, perhaps a container on a virtual machine, and gets executed, which means that we can execute arbitrary commands into a serverless function if the vulnerability presents itself. So I'm going to show how we're going to do that today. Don't worry. I have not discovered an open SSH port on all of our containers for our serverless environment. This is a little bit more nuanced. And to explain what I mean by that, I'm going to describe and review two types of attacks that exist in the application security world. The first one is command injection. So injection is a large umbrella of different vulnerabilities. And this happens anytime you have an application taking in data that could potentially be sent to a subsystem. So this can happen with a SQL database. It can happen with an LDAP database. It can even happen when you take user data and feed it to a command line. So this is where the problem lies. If you don't handle that user data properly, in the process of sending the data to the subsystem may be tricked into interpreting that data as actual code. We've seen the damage that can be done with SQL injection and several other types of injection attacks. But you can also do it with OS injection, where you take user data and put it in a command line command. Now, thankfully, a lot of serverless applications are not doing this. I have not seen many serverless applications that run a shell command as a result of some API call, but they exist in more traditional applications, which is why the focus of this talk is going to be more about the supply chain attack. So what do I mean by supply chain attack? What I mean to say is there are many components that we build our application out of. I heard a statistic recently that says that 97% of the code that we deploy to Node.js ecosystems is not code that we write. 3% of it is custom code that your company's writing. 97% of that code is coming from open source repositories such as npmjs.org. So what is the probability that one of those dependencies gets either a command injection vulnerability or is just compromised? The answer to that question is 100%, because it's already happened. It happened to ESLint in the summer of 2018, where ESLint, an incredibly powerful library, was compromised to then steal AWS credentials from a variety of different workstations. And this was a huge problem. So this can and will happen again. And this slide goes into some details on how you can do what's called component analysis to prevent this problem. We'll talk a little bit more about that at the end. But those are the two types of attacks that you can utilize in order to execute arbitrary commands on a serverless server. Now this presentation is less about how you get the code onto the serverless servers and more about what risk is associated once you have shell on a serverless server. So in order to demonstrate that risk, we are going to introduce a new tool that I helped co-author. Introducing Puma Security's Serverless Prey. This is an open source repository that allows you to send out vulnerable functions to your various cloud providers, and those functions are going to establish a reverse TCP shell to a server that you control, waiting to execute various commands. Now, I've written this with a friend of mine and fellow SANS instructor, Eric Johnson. Just to clear this up, there's another Eric Johnson at this conference. It's not this Eric Johnson. That guy's a really nice guy, seems to know what he's talking about. Unfortunately, he's presenting right now in the other room. So definitely check out his video later. Check out this presentation right now. But different Eric Johnson. So he works for a company called Puma Security. So the theme of this is all big cats of prey. So we have Panther for AWS, Cougar for Azure Functions, and Cheetah for Google Cloud Functions. So I'm going to give you a brief overview of how this technology works, and then the rest of the presentation is going to consist of us actually hacking these services and servers using this technology. So here's a bit of a technical diagram of what we're going to be doing. I've already done step one. I have deployed the serverless prey functions to the 3 cloud providers that I want to attack. So this is simulating the process of an attack. A real attacker would not actually deploy this function. They would use command injection or a supply chain attack to do a similar thing. We're going to use this to simulate the attack. Steps 2 through 5 are going to happen here live in a minute, hopefully, if the demo gods are smiling upon me. But we're going to set up a server called a Netcat server. Netcat is a fairly simple utility that basically allows you to connect 2 machines and send data between the 2 of them via the command line. You'll see why that's important in just a minute. My Netcat listener is not going to be exposed on the public internet by default. So we're going to use a tool called ngrok to forward that port to the public internet such that our functions can reach out. Then we are going to invoke the function with the data it needs to call back to our local server. And finally, the function is going to reach out to our Netcat listener, listen for data, and whatever we put over the wire, it is going to execute in a bash shell. So TLDR, it's basically an SSH daemon for serverless. Obviously, this is a simplification, but that is the idea. And without further ado, let's actually demonstrate this. So I am going to open up my terminal. And from here, I'm going to run this Panther script. I'll explain what it does in just a moment. After a second, after the cold start happens, I should have shell. I'm going to type ID to see what my user is. I'm in. So all of those steps have happened at once. Steps 2 through 4. And I know that this is kind of hard to see on the screen, so I'm going to move it over just a bit. Steps 2 through 4. We're setting up a Netcat listener. We're listening for commands on the server side. And whatever command I type in here is going to go through. You may notice periodically this connection terminated restarting message. And there's a good reason for that. Why do you think my function is restarting approximately every 30 seconds? Timeouts. Exactly. So API Gateway has a maximum timeout of 30 seconds. So to keep this session alive, my shell script is automatically reconnecting to the server. So now we're going to make this talk really interactive. I want to call on the audience to tell me some commands you'd like to run as an attacker. You've gotten shell in a server. What do you want to do to start wreaking havoc? Pardon? Sudo rmrf. Good answer. Unfortunately, as you can see here, I am not a root user, and I am not a sudoer. More importantly, the file system is read-only, except for one exception, which we're going to go into in a minute. What are some other things we can do once we've gotten root on, or gotten shell on a server? Look in var log, certainly. We can look at a variety of logs. Before we go into the log material, how about we figure out where we actually landed, what directory we're in? So I'm going to type pwd. So we're in this var/task directory. I wonder what's in there. I'm going to type ls. Turns out I have two files, config.json and handler.js. Let's start with the second one. What do you think the handler.js file is? The Lambda function, absolutely. So let me cat handler.js. I now have all of the source code associated with this Lambda. This has a variety of different implications. This may have intellectual property concerns, because now I have your function and I can reuse it in my own application if I wanted to. Furthermore, there might be secrets in this file. So that's pretty dangerous. At minimum, I can look at this function and reverse engineer it to maybe do some other kinds of attacks. So let's take a look at that other file, config.json. This one actually has credentials in it. So these are credentials to a database. Now, a lot of people might be thinking, oh, OK, this function connection is only temporary. So what's the big deal? Are those credentials temporary? Depends. Depends if you're rotating them. Likely not. How many times do you rotate your SQL database password? 0 times a year, probably. Let's be realistic. So this is pretty dangerous stuff. So I mentioned earlier that we cannot write to or modify any directory in the serverless container. There's one exception to this. Does anybody know what the one directory we can write to is? Temp. And why is that? It's because we need to be able to do some basic file processing within the Lambda. So they give you that directory to work with. So I wonder if we can write files to that directory, perhaps malware to that directory, and then use it later. So let's see that in action. I'm going to go to the temp directory, and I'm going to echo "you got hacked" to this file. And if I ls now, that file is actually there. I'm going to plug my charger in because I'm about to run out of batteries. So you may be thinking, oh, this function is going to go away in 30 seconds, and that file is no longer going to be there. Unfortunately, that is not the case. And we'll see this when it restarts, which I think just happened. I'm going to type ls again. Oh, ls in the temp directory. The file's still there. Now, why is that? The reason is because of cold starts versus warm lambdas. So everybody thinks, OK, you're starting up a new container for every invocation of a function. And that's simply not the case. If that was the case, every single Lambda invocation would be a cold start, which takes a very long time to do. For performance purposes, AWS makes it so that every time you invoke a function, it will stay warm for a period of time, meaning it will reuse that container, which saves a lot of time. But it also means that the file system ends up being persistent. And this is a big problem, not only because of the fact that I'm keeping this container warm myself, but sometimes developers keep their containers warm on purpose. There's a warm-up plugin that actually exists in the serverless framework. And with that plugin, it keeps the function alive indefinitely in order to benefit from the performance of not having cold starts. That also means that our malware would be persisted long term. So that's some scary stuff to be aware of. We're just trying to analyze the risk of accessing these environments. So now I'm going to show another kind of attack that's particularly interesting. Who here is aware of what I mean when I say IAM policy? Yeah, I'm hoping everybody in the room raises their hand because this is a very important subject that a lot of people overlook. So when your function starts up, it is given permission to access other AWS services, such as maybe S3, maybe a database. It's given a lot of permissions. In order to do that, it's giving it over an environment variable. Now that I have shell on this Lambda, can I just read those environment variables? Let's do it. env. Boom. That's everything. In fact, I can disconnect right now. I don't even need to be in the function anymore because these credentials are going to live for quite some time. Let me demonstrate the damage that can be done with these credentials. So in this terminal, I'm going to try to download a secret file called panther.jpg. Obviously, it's not really a secret, but for the purposes of demonstration, imagine that this was a sensitive file that was in a bucket that is not publicly accessible. I do not have any credentials right now. So when I hit enter, I'm going to get a 400. Fatal error because I don't have the necessary credentials. But all I have to do is copy this data from here to there, and once I do that, I am going to have this file. So bear with me as I do a lot of copying and pasting. And even though the container might have died at this point, these credentials are still good for quite some time. So that's 2. I need 3 different values. Last thing I need is the session token. Right over here. Oh yeah, there we go. And here goes nothing. We now have successfully downloaded that file. Let's take a look at what we've just pilfered. Just a Panther. But imagine the damage that could be done here. So for the sake of time, let's move on to another environment. We are now out of AWS, and we are going to Google. Now, Google's interesting. They actually have their containers running as root by default, which is very bad practice for those who know about container security. So in order to get this done in 3 minutes, I'm going to go right to the same exploit that we just demonstrated. You don't get to get your environment, you're not able to get your credentials via an environment variable like you can in AWS, but you can trivially do so using one of these curl requests. So here I'm going to get a token from Google to have the same role as the function. And unfortunately, Google's permission setup is ridiculous. You can do functionally anything by default in a Google function. In AWS and in Azure, you say, here are the specific things I want to accomplish. Here are the exact permissions that I want to give. In Google, by default, you can do basically anything other than changing your billing. So that's really terrifying. So let's see an example of this. I'm going to take this access token, and I'm going to copy it for my next command. And again, I can exit out of this session. Doesn't matter if I'm still connected to the Lambda or not. I'm going to go over here. Right now, I don't have a token in this curl request. So when I curl this, it's going to say that it downloaded, but when I look at the file, it says invalid credentials. I'm going to repeat this attack with the credentials I just got from the Google container. And let's open that file. There's the cheetah. All right. So those are 2 of the 3 environments. Azure is kind of weird because there are many different ways you can deploy an Azure function. You can deploy one that is Linux-based or Windows-based. So for the sake of time, let's get into the Linux server as fast as we can. Those cold starts are painful, I gotta say. There we go. Come on, wake up. There we go. We're alive here. So very similar process. We are going to get some data from the container. And we're going to take that data and put it in another request. Going to adjust the view here, make sure I copy exactly the right amount of data, and going to paste that here. Going to cat this file, or open this file, sorry. There's the cougar. So now we've shown how you can steal sensitive resources from any of these 3 environments if you have one of these types of attacks. There's also a Windows shell that you can utilize in our code base if you'd like, but you get the picture of what kind of damage we can do. We can read files, we can write files that can do other things, and we can get those very important credentials. I keep kicking my charger. So to wrap this up in the last minute, I'm going to give you a little bit of detail about the remediation steps. So the number one thing is limiting your policies. You should not give your functions more permissions than they need in order to get the job done. And the same thing goes for your network access. If there's a resource that doesn't need to be on the public internet or accessible by your function, let's lock it down. And a lot of this comes down to automation. We need to find permissions that are overly permissive and remove them, as well as look for issues that we find in our packages. But lastly, we have to accept the fact that there will be zero-day issues that happen with our packages. Packages that are compromised that we don't know about until it's too late. That's where runtime security solutions are very valuable. Solutions that can actually prevent the runtime from doing actions that it otherwise would be allowed to do. So just straight up blocking certain types of outbound HTTP or file writing or process generation, for example. And the last part of that is about monitoring. The things that we can't prevent, we have to be able to detect. So that might have whetted your appetite. If you're interested in learning more about the defensive part of this equation, you can check out the sister talk to this presentation, Defending Serverless Infrastructure in the Cloud, which was done by Eric Johnson earlier this week at the RSA conference. There's another talk happening at this conference in an hour that you can watch about security in serverless, and I've already watched a previous version of that talk, and it's quite good. And then finally, if you'd like to learn more about the differences between the different cloud providers, I've done a webcast recently for the SANS Institute that goes into a lot more depth about the different things that are happening in our various serverless providers and our various cloud providers in general. Finally, here's the code base for Serverless Prey. We'd love to take some pull requests and to get your feedback on this project. With that, I know I'm over time, so I'm going to answer questions outside of this presentation. You can get me outside of the room, and thank you so much for having me.